up bringing the accommodations for the out-of-town guests and such. And so now I will hand things over to Umesh, who'll give a little introductory remarks to the workshop.
Thanks, Andy. Welcome, everyone. So since, I mean, most of you are old hands here, but I guess many of you are here just for this workshop. So I'll say a little bit about quantum and Simons and also this workshop. So, I'm sure many of you know there's that we run something called the Quantum Research Board here at the Simons Institute, which is a continuous presence of people who work in quantum computing. There are a number of postdocs, visitors, students, etc., who are here on a permanent basis. And then in addition to that, we run summer clusters like the one that this workshop is a part of this summer. And there's an upcoming program next spring, which is actually a co-location of coding theory and two programs, one in coding theory and one in quantum computation. So again, if you're not already participating, there are going to be several workshops during that semester, and you're welcome to participate. I should say a little bit about this summer cluster. It's been funded by NSF and DOE as part of this National Quantum Initiative, and part of the rationale for this is actually to have closer ties between quantum computing and the computer science community, the theoretical computer science community. Now, anybody who hears that should be a little startled, because of course theoretical computer science was right at the heart of the beginning of quantum computing. So what does it mean, closer ties between theoretical computer science community and quantum computing? Well, I guess the point is that there's a real barrier to entry for computer scientists to go into this field because of having to learn about quantum mechanics. But on the other hand, the reasons to try have become now almost impossible to resist. So, for example, the ties between quantum computing and cryptography are now so deep that it's really hard to imagine working in the field without understanding these connections. Or if you look at STPs and the connection to quantum and complexity theories, again very deep and interesting. Or if you look at algorithms for linear algebra, again there are these deep connections. So what the Simons Institute has been trying to do is to sort of provide a catalyst for bringing these together. And there's another aspect of this of what it's trying to do, which is to also nurture connections between quantum computing, from the computer science side, and physics and chemistry and mathematics. And okay, so maybe you'll see some of the themes here in this workshop. So each of the days is designated to be a different topic. We've tried to keep the workshop extremely relaxed, with only 4 talks a day, each an hour long, and with lots of breaks. So some of you may remember, very few of you may remember, that the first workshop at the Simons Institute was on quantum computing back in 2013, maybe. And there we had this rule saying that discussion trumps schedule. So that has two components to it. One is that you should feel free to interrupt and ask questions. There's each session has a moderator, a session chair, who will stop you if you're going too far off on a tangent. But then it also comes with a promise to the speaker saying that any amount of time that goes into these questions and answering them is not taken out of their time. We'll just let the schedule sort of slip as need be. Okay, so discussion is more important than keeping the trains running on time is the main. Okay, so as Sandy pointed out, Bill has done some of the heavy lifting on putting the workshop together. What she failed to mention is that she's one of the organizers of this program and of the workshop. So it was Sandy and Urmila Mahadev and Chinmay Nirke and of course Bill. So Bill's chairing the session, so I'll hand it over to him.
Okay, thanks, Umesh. So yeah, I'm the session chair. Like Umesh said, each day has a particular theme, and today's theme is all about quantum advantage and quantum benchmarking. And of course, it's really hard to imagine getting started with in a sort of a better place than to have Scott Aaronson from UT Austin, sort of a seminal figure in the field, of course, tell us about his wish list for verifiable NISQ experiments. Scott.
All right. Well, thank you so much, Sandy and Umesh and Bill. And it's always a pleasure to be able to be here at Simons. And this image, I asked, I now work for OpenAI, of course, so I had to ask Dolly, what is your solution to verifiable NISQ advantage? I'm not, this was its answer. I'm not sure if there's any insight to be gleaned from it. But this talk is less a talk of like, here's, some difficult results that I proved that I'm proud of and that I want to, show you or brag about. I mean, there will be some results, but mostly, this is a talk of here is what I would like you to do, while I'm off, trying to save the world from the robot apocalypse or whatever. Okay, the truly important stuff like quantum complexity theory, still needs to happen. And so here is what I would like to see happen. And so it's sort of a research program which any of you can have free of charge. So I know that most of you know this, but just to sort of briefly, recap, where are we on the quest to demonstrate quantum supremacy or quantum advantage or whatever you prefer to call it? Let's say 13 years ago, some of us, including, Bremner, Joza, and Shepard, independently, me and Alex Arkhipov, had the realization that if your goal is just to demonstrate a speed up via a quantum computer, as soon as possible, then you sort of don't want something like Shor's factoring algorithm, that will clearly require a fault tolerant hardware, and that we can't implement. We don't know how to implement yet. What you probably want to do is a sampling task. Okay, a task that does not have a single right answer, like factoring. Okay, where the desired output is a sample from a probability distribution. Okay, and you can design problems like that are extremely close to the native hardware, right? That are that don't require very expensive encodings. And then you're sort of playing a game of, you get to shoot an arrow and then sort of draw the target around where it landed, right? You don't care which specific distribution you're sampling from, as long as it is some distribution that you can characterize and that you can demonstrate that you are sampling from it, and you can give evidence that doing the same thing with a classical computer would be hard. Okay, so there are two main types of experiments of this form that have been actually done on a large scale, over the last 4 years or so. The first of these, actually the first one to be achieved experimentally was random circuit sampling, which, in the way that we now reckon time, was announced by Google just before the pandemic. And they built a superconducting device called Sycamore with 53 qubits, actually 54, but one of them didn't work, in a rectangular array. And they have controllable nearest neighbor couplings. So they have 2 qubit gates in these sorts of patterns. And then all they do is they start with the qubits in the 0 state and they apply a random circuit. Okay, but they apply the same random circuit over and over again. And, and then each time they measure and they get a sample from some probability distribution over 53-bit strings. Okay, and they repeat that millions of times. And they collect a lot of data. And then they have the problem of how do you validate that, right? How do you know that your quantum computer did anything interesting? Okay, and so we're going to talk a lot about the problem of validation, which is really key to this entire enterprise. Okay, and then, but then the second question, of course, which is also key, is well, was there, however whatever validation test you're using, could a classical computer have passed that test as well? Could a classical computer have spoofed it? Okay, and there's been a lot of discussion back and forth about that question. And these problems are not as hard for a classical computer, as it turns out, as one might have originally hoped they were. Okay, but if your goal was to solve this sort of bizarre sampling problem, I think that there are still a couple orders of magnitude advantage to actually doing it with a quantum computer as opposed to doing it by any currently known classical method. It's not clear whether that will continue to be true. Okay, so you could say we still we have quantum supremacy, quote unquote, but it's sort of hanging by a thin thread, and there is an urgent need to do better. Okay, now. The other type of experiment that we've seen over the past few years, during the pandemic, actually, was large-scale experiments in boson sampling. This was the thing that Arkhipov and I originally proposed in 2011. It's where you generate a bunch of photons, you send them through a network of beam splitters and phase shifters, so just simple linear optical elements, and then you just measure. You have a bunch of photodetectors that that see like in each output mode, either is there a photon there, how many photons are there, and so you get a sample from a probability distribution over all of the possible places where the photons could have ended up. The surprise to people was that this simple linear optical setup, even without feed forward measurements or anything like that, it's almost certainly it's not a universal quantum computer or even a universal classical computer for that matter. But if you look at how hard would it be to simulate classically, we could give an argument that well, at least to do it perfectly seems to be very, very hard. An argument related to the fact that linear optical amplitudes are the permanence of matrices, n by n matrices, if you've got n photons, and the permanent is a sharp P complete problem in complexity theory. Okay, so we're not saying, we weren't saying that boson sampling itself lets you solve a sharp P complete problem. Like that would be too good to be true. But because the permanent is sharp P complete, you can use that to argue for why even just simulating the sampling task that this device is doing seems to be classically hard. Okay, so again, there's been a very interesting interaction here where first, the team at USTC in Hefei in China, led by Xiaoyang Liu, announced in 2020 that they could do boson sampling, or a variant called Gaussian boson sampling with about 100 photons on average. And and that they did not know how to simulate the results classically. And since then, the group at Xanadu in Toronto has also done a boson sampling experiment, which improves over USTCs in that it has controllable beam splitters, and also they can actually count how many photons are in each output mode rather than just saying is the number 0 or non-zero. Now, there's also been, people trying to simulate these experiments classically, and including some, people in this room who have worked on that problem, and we might hear more about it. And I would say that it's not clear if we have quantum supremacy right now with boson sampling. One of the big engineering problems is that a large fraction of the photons get lost as they're traveling through the beam splitter network, and it would be much easier to argue for the classical hardness of what is going on if we could do this without so many lost photons. Yes.
When you say quantum supremacy, you mean just count the time for the particular task and that's it?
Yeah, so we should be clear that this is a soft criterion. Like, it is a thing that, like, you could be in a world where it's definitely not achieved. You could be in a world where it definitely is achieved, like, no matter how you look at it. But you could also be in, like, the BPP intermediate regime where you can't.
Also be in a changing world. I mean, it's
That's right. And you could even have quantum supremacy be achieved and then unachieved, because the classical computers get stronger, right? So fundamentally, we're asking for something negative, right? We're asking for, there is not a fast classical algorithm to do this, and classical computing can fight back. I mean, so this is a fundamental difficulty, and I feel like right now we are right in the middle of the sort of the BPP, intermediate era, when you can still, it depends what you mean, and you can argue about it. Now if you look at, let's say, the superconducting, the random circuit sampling experiments, I think that if you so you can always simulate them faster classically by just using more cores, right? So this is the fundamental difficulty in using wall clock time, as your measure, right? You can always just pay more to AWS or whatever, right? Just buy more parallel processors, right? And the simulation methods that we know are all highly parallelizable, right? And so you can always reduce the classical time by just spending more and more processors. But then you could compare the amount of energy, right? And a superconducting quantum computer like this one is not exactly green, right? It uses a dilution refrigerator, right, which is the size of a closet, and which is pretty energy expensive. But if actually, John Martinez and I, tried to run the numbers, and I think that there's, looks like there's at least a factor of 100, compared to, if you wanted to simulate this classically with like the best known algorithms and reproduce the same linear cross entropy score, right? We know very fast algorithms like those of Barak et al. That would get a worse linear cross entropy score. But if you want the same one, as I said, there seems to still be an advantage, albeit a tenuous one. Yeah.
I find it a little troubling, this way of looking at things, where you say, well, quantum supremacy, you achieve it, you unachieve it. It sort of depends upon the side of it that you wake up on. And, it depends on sort of these very fine margins.
Yes, of course it's troubling.
I've never seen it like that. For me, the Google experiment was plausibly, you could sort of make a case that maybe they had achieved quantum supremacy at the time that it was announced, and that was great. I think that's a fine thing to claim. Mm-hmm. But I think that when one thinks about quantum supremacy, one means, look, the margins are so great that barring a revolution in our so for instance, we prove P equal to NP. Okay, great, all bets are off, right? So, but I would imagine that it's something where we say, barring a real, change in, some sort of revolutionary change in our understanding of the field, we've achieved it.
Yeah, so I mean, of course it's troubling, but at some point it's a terminological issue, right? Like I didn't like the term, quantum supremacy when it was right? It sounded too self-aggrandizing, when I first heard it, and then people said that you should stop using it. Then I felt like, okay, well then I will use it. But you could say, maybe it's all, this is all clearer if we just say quantum advantage, right? There is there seems to be an advantage if your goal was to solve, random circuit sampling or, get a high linear cross entropy benchmark, right? There seems to be a modest advantage to using the device. The advantage is marginal. One more improvement in the classical algorithms and it could be gone. Yes. On the other hand, we could probably, with today's technology, we could do a much better random circuit sampling experiment.
So I would propose that, as you said, the term quantum supremacy seems, very strong. So let's keep it strong and say, look, you don't achieve it, and let's say quantum advantage means exactly what you said, that, if we think that there's an advantage.
Sure.
Yeah, but
What was your problem? Eddie.
that they had an architecture which was going to give rise to a universal quantum computer. So their claim was stronger just than that they achieved advantage, but they did an architecture which had controllable qubits, which could lead to a universal quantum computer. And that was a very important part of the claim.
I agree.
And that is part of the story here, is that they're saying that a universal quantum computer can achieve advantage, not just a random physics experiment.
I agree. No, it's not the part of the story that I was focusing on, but it is an important part. Yes. Okay. All right. So just to be a little bit more precise, what was the random circuit sampling proposal? You challenge the quantum computer by sending it a randomly generated circuit C on n qubits. Then you ask the quantum computer to send back to you quickly a bunch of what ought to be independent samples, call them S1 up to S sub k, from a distribution that we'll call D sub C, right? Which is just the distribution over n-bit strings that you obtain by applying C to the all zero initial state. Okay, so now this is a distribution, that depends on the circuit. Given enough time, you could compute it if you knew the circuit. Okay, and it's not the uniform distribution, right? It has little inhomogeneities in it. Okay, because some amplitudes are a little bit bigger and some are a little bit smaller, right? So some randomly enjoyed more constructive interference and others suffered more destructive interference. In fact, the amplitudes look like IID Gaussian random variables, more or less. Okay, and so what that means is the probabilities, they're all exponentially small, with overwhelming probability, but they're not all equally exponentially small. Okay, some of them might be 2 over 2 to the n, others might be only a half over 2 to the n, and so forth. And those inhomogeneities are the main thing that we're interested in. Okay, now how do we detect them? Yeah, so we use a staggered pattern like this in our random circuit to make sure that every qubit can influence every other one. And then what we do is what became known as the linear cross entropy benchmark, even though it's not actually about entropy. So we using our knowledge of C and using our classical computer, we calculate this sum here. Okay, so for each of the observed outputs, S1, S2, and so forth, we calculate what would have been the probability that an ideal quantum computer would have produced that as output. And then we just sum all of those probabilities up. Okay, and if the sum exceeds a certain threshold, then we say that, the experiment succeeded and otherwise not. Okay, so now what should that threshold be? Well, clearly the average probability is 2 to the minus n. They add up to 1. So if we just pick the SIs uniformly at random, we'd expect the sum to be about k over 2 to the n. Okay, and so now the key question is, are we exceeding that? And by how much are we exceeding it, right? And now you can do a calculation that says if you had an ideal quantum computer, then what you would expect for this sum is that it would be about 2k over 2 to the n. Okay, so that you would satisfy this inequality with b equal to 2. Okay, and again, with just trivial coin flipping, you would achieve b equal to 1, right? And so now what Google achieved in its experiment in 2019 was b equal to 1.002. Okay, so it's a situation that's actually very, very analogous to the violation, the experiments that violated the Bell inequality, starting 40 years ago. Okay, so you have the ideal quantum value that you sort of that you can't achieve. You have the trivial classical value that's not interesting to achieve, and you're trying to just exceed the classical value by even just a little bit, and thereby, hopefully rule out any secretly classical explanation for what was observed. Okay, So, okay, but now, what is wrong with the current experiments? Well, we already talked about this somewhat, but, okay, the obvious problem, you could say, is that the lack of error correction, in our device sort of prevents scaling it up to the regime where, the quantum advantage would really be unambiguous, where we wouldn't have to squint and argue about it anymore. Okay, so right now, you can, in Google's experiment, they did 2-qubit gates with maybe 99.8% fidelity. Okay, apparently now you can do a 2-qubit gate with 99.9% fidelity. And oh no, sorry, Google maybe had 99.5%. Yeah, I'm sorry, it's all right. And then it more recently it got up to 99.8 and then 99.9, which is part of why I say that a much better random circuit sampling experiment could be done right now than was done a few years ago. But then you're applying about 1,000 of these gates, and because there's no error correction, the total circuit fidelity falls off exponentially, right? With it goes down and down with each new gate that you apply. In Google's experiment, there was maybe on the order of 1,000 gates. And scientifically, one of the most interesting things that we learned from the Google experiment was that the total circuit fidelity seemed to scale simply like the fidelity of one individual gate raised to the power of how many gates there are, right? And so if there are some sort of conspiratorial correlations that push the fidelity down further, then we seem to see no sign of it. Okay, and this is interesting enough that Gil Kalai, for example, still does not believe it, right? And he basically, has a 40-page paper saying like, this is impossible. There must have been, something wrong with the experiment because that's just, too good to be true. But in the meantime, not only Google, but also, USDC and I believe, IBM and others have now replicated it. So, okay, but having said that, as long as the circuit fidelity is going down exponentially with the number of gates, then you can see that you're sort of inherently limited, right? You could do 50 qubits, maybe you could do 100 qubits, right? But you can't do millions of gates on thousands of qubits. Because if you do, then what you get out at the end will just be indistinguishable from the uniform distribution. Okay, and so now so this is sort of what limits us, right? You're limited to, let's say 50, 60, 70 qubits, maybe 20 or 30 layers of gates. And in that regime, you can be clever. You can do, classically a little bit better than brute force at simulating these things, or even a lot, still exponential time, but a lot better than brute force. And if you're clever enough, then you may be able to defeat the claim of quantum advantage. But to my mind, though, there's an even deeper problem than that, which is that even if you could scale, even if suppose we had hardware that was good enough that we could scale to hundreds of qubits and thousands of layers of gates, even then it's still not clear how we would do the random circuit sampling experiment because we wouldn't know how to verify the result. Okay, the verification of the result using this linear cross entropy benchmark, right, requires that we calculate this number here, right, which means we have to calculate this sum, right, and that seems to be hard for a classical computer for exactly the same reasons why we believe that spoofing the experiment is hard. Right, and so the verification and the spoofing are linked to each other, right? And so you can't go completely beyond the realm where a classical computer would have any hope of spoofing you, because if you did, then you would also be completely beyond the realm where you have any hope of verifying the results. Okay, so that's really an inherent problem with this type of experiment. And so what I think has emerged over the last couple of years as maybe sort of the central, near-term challenge for quantum computing theory is, can you solve that? Can you get a sort of so you could say that what we want is a quantum speed up that has 3 properties simultaneously. Okay, so let's go through these. Okay, this is how I think about sort of what I would like to be a central research agenda for the field. Okay, we want a quantum speed up, which on the one hand is NISQ. NISQ is of course means noisy intermediate scale quantum. Is a term that John Preskill coined 6 years ago. And again, like quantum supremacy, it's not exactly clear what its definition is, but you could say, we sort of know it when we say it, right? Or we know it when we implement it. Okay, NISQ means things that we can actually do on quantum computers that will be available, now or in the next few years, and that do not require error correction or at most only very, very minimal error correction. Okay. And then the second thing is, of course, at least in principle, we would like a quantum advantage, which means we need some argument or some evidence that there is not a fast classical algorithm to do the same thing. Okay. And then the third thing that we want is the one that I just talked about. Okay, that we want an experiment where a classical computer can efficiently verify the output, where we don't have to do an exponential time classical computation, like to calculate a linear cross entropy score or something like that. And therefore, there is at least the potential that we could scale the experiment up to hundreds of qubits, as are available on some of the latest devices. Okay, and my claim is that our knowledge right now is that basically we know how to achieve any 2 of these 3 requirements. Okay, so if you ask for something that is NISQ and has an in-principle quantum advantage, then that's exactly the current generation of sampling-based quantum supremacy experiments. Boson sampling, random circuit sampling, things like that. If you ask for something that has an in-principle quantum advantage and is efficiently verifiable, well, I mean, those were some of the seminal early discoveries of the field. Shor's algorithm, presumably gives you that, right? A solution to factoring or discrete log is efficiently verifiable. Those are NP problems. But there are other things in this region as well, right? And there were breakthrough recent protocols for taking arbitrary quantum computations and making them verifiable by a classical skeptic using cryptography and using interactive protocols. Okay, the big breakthrough was that of Ermol Mahadev, and there's been a lot of work since then building on that, trying to make it more practical, and maybe someday that will get to the NISQ era, but or be implementable on a NISQ device. But I think that we're not there yet. Yeah.
I'm not sure this is exactly consistent with your definition of supremacy or of advantage.
Okay.
Because, if you look at advantage as at a given point, a given task is, a quantum computer wins over a classical computer, then you don't need scalability.
Yeah.
So if you give up scalability, then you don't need efficient verifiability.
Well, okay. I mean, I would say that I kind of want both things. I want to see that. Well, okay. I would say that I want 3 things. Okay, because I should have had a slide about this. But I want you to beat a classical computer. In the most concrete sense of just here's the numbers, here's the resources, the energy, the time that we needed, right? And we are winning. Okay. I want it to be for a general problem where we believe that there is an asymptotic speed up. Okay. And thirdly, I want the explanation, the only available explanation of number 1 to make reference to number 2. Okay? So I want the real world speed up that you've observed in practice to be in some sense because you are solving a problem that has an asymptotic quantum speed up.
Then why tie the 2 things together? I mean, you could imagine quantum advantage being shown as evidence for scalable quantum supremacy, even if the constants are still, in favor of the classical computer.
You could. I mean, that would be a weaker thing to aim for, and then, the skeptics will then endlessly make fun of you. But I mean, you could, right? I mean, like yes, you could, along the way toward achieving this, you could achieve that weaker thing. I'm just setting my sights a little bit higher than that. Okay. So now a third thing in this intersection might be physics simulations, where here the verification would not be because the problem is in NP necessarily, or because of any clever interactive protocol, but rather it would be because you can take the result of your quantum simulation and compare it to experiment. You can compare it to, what is actually the rate of this chemical reaction, or what is actually the, magnetic susceptibility of this material, right? And you could see if your simulation is matching experiment. Okay, so I have some optimism that something here might be doable in the NISQ era. But then if we ask for the intersection of these two bubbles, something that is NISQ and efficiently verifiable, I would say that all the work that there's been over the past decade on sort of NISQ quantum optimization methods, such as the QAOA or VQE and various quantum machine learning algorithms, I would say if we could be confident that they are beating a classical computer at some task, then this would get us to where we want it, right? I think the challenge here is, of course, as people working on these things very well know, is to get a clear speed up over classical. Okay, so just looking at this diagram, gives us three obvious strategies for sort of trying to get into the center of this Venn diagram. We could start with the heuristic algorithms for optimization and machine learning problems like QAOA, and we could try to show or find the problems on which they give us a clear quantum advantage if there are such problems. We could start with protocols, including cryptography-based protocols or physics simulations that we're pretty sure give us a verifiable and scalable quantum advantage, and find a way to implement these on a NISQ device. But I would say right now a big difficulty is that anything that involves doing cryptography on a superposition over inputs, okay, anything that looks like that, that involves doing number theory or lattice computations or anything of that kind in coherent superposition, seems like it is beyond what we can do on a NISQ device right now. Okay, I think that some further insight or optimization will be needed to change that situation. Okay, but that's the second thing. And then the third thing is like the one I guess that I've personally thought about the most. Could we take the kinds of quantum supremacy experiments that are already successful, that we already know how to do, and figure out a way to make them efficiently classically verifiable?
But do you treat them as in principle quantum advantage still?
Yes, in principle. Yes.
Despite despite what you said in the beginning.
Yeah, I mean, because all of the efficient classical simulations that we know sort of use the way in which these experiments are imperfect in various ways, right? They use the fact that the fidelity is imperfect, or that in the case of boson sampling that many of the photons are lost. Right? I mean, the ideal versions of these experiments, we're still quite confident that there should be a scalable quantum advantage there. So, all right. So I've been thinking about, I don't have a solution to this, but I have at least a research program that looks of problems that look like one could make progress on them, and that would give us new very relevant new information about this problem. So I want to tell you what my new open questions are. Okay, so let me call a quantum circuit peaked. You know what? Yeah, all right. Yeah. All right. Let me call a quantum circuit peaked. I was just checking if people were paying attention. Okay. If it has the property that there is some output, there is some string X that C outputs with a very large probability, like let's say at least 1/10, when what? If C is the identity, then it would be peaked, with X equal to the all zero string being the string on which it is peaked. Yes, it is easy to give examples of peaked circuits, right? Okay, good. Thank you, Eddie. So now what one could give a more general definition. What I really care about here is just, does the state produced by C, so C 0 to the n, does it have sort of any features that make it easy to distinguish from just the maximally mixed state, or just let's say a Haar random state? Okay, but this would be one of the simplest examples of such a feature, right? If it has a very a noticeable probability on a single string when it is measured in the standard basis. Okay, so now let me ask the following question. Okay, suppose that I pick a random quantum circuit with, let's say, n qubits and n squared gates, some fixed polynomial in n number of gates. Okay, so I pick a random such circuit, and then I condition on the event that the circuit is peaked. Okay, so I throw away the circuit unless it happens to be peaked. Right, and I only look at the peaked ones. Okay, and now my question is, what does a random peaked circuit look like? Okay, so like what kind of structure does it have, if any? Okay, so let me give you sort of two extreme possibilities, just to so one possibility would be that it looks like this. Okay, so you could always get a peaked circuit, as Eddie said, by implementing the identity, right? Which you could do by just applying any circuit you like, say U, and then applying its inverse, right? So it could be that, you just, a random peaked circuit just looks like a very complicated implementation of the identity or of some other classical function where, just by taking the gates in that circuit and canceling them against each other using a classical computer, it would be trivial to see what was going on, right? To see that, nothing too interesting was happening. Okay, now a second possibility would be that a random peaked circuit would be indistinguishable by any efficient classical algorithm from just a uniformly random circuit of the same size. Okay, so you wouldn't know, with a classical computer, at least, you wouldn't notice anything unusual about it, or anything special. And yet, if you ran it on a quantum computer, then it would just so happen to choreograph the right interference pattern in order to end up at one of these peaked states. Right? Now, what is the relevance to verifiable quantum supremacy? Well, I care a lot sort of which world is true. Okay, because if this second world was true, then what this would be telling us is that sort of the circuits that we want for verifiable NISQ quantum supremacy experiments are out there. Okay, at least they exist, platonically, right? It would, we want circuits that kind of look like random circuits, because those are the kind that we know how to implement with 60 or 70 qubits, but that actually concentrate all their amplitudes secretly on a particular outcome, right? Which we could then design a quantum supremacy experiment around. So for example, this would then merely leave us with the problem of how do we find such a circuit efficiently, right? If we could find these circuits efficiently, then this would give us our quantum supremacy experiment. Namely, I give you such a circuit and you have to decide, is this a truly random quantum circuit or is it a random peaked circuit? Right? Clearly, a quantum computer could solve that decision problem, and you would just see the answer when you ran it. You wouldn't need an expensive classical computation. And by assumption, a classical computer would not be able to solve that problem. Yeah. All right.
Why is it clear that if it looked random, then it would be robust?
Well, okay. I mean, there's still the question of robustness to noise, right?
So yeah, I mean, it's not that. So the thing that you started with this notion that we know how to implement random circuits.
Yeah.
But we also know how to implement non-random circuits. It's just that they are not robust. Neither the random ones nor the non-random ones are robust.
Yeah. Well, I mean, one way to explain the question is, I would like to know whether you can get a big quantum speed up for some problem without sort of doing some sort of expensive encoding of a different problem into that one. But that's not that question is not so easy to formalize, right? So I am substituting the question of can you get a big quantum advantage from a circuit that classically you could not even distinguish from a random circuit. Okay, so I'm asking, with a quantum circuit that looks random, that has no classically noticeable structure to it, right? Is that already enough to see a quantum advantage? Okay, so I mean, of course, this is not the only possible approach to NISQ quantum supremacy, but I claim that this is one approach. Okay, and in some sense, I'm asking a question here that goes back to the very beginnings of quantum computing theory, right? Of like just how much structure do you need, right, to get a quantum speed up, right? And it's a question that it's the question that I was trying to address when I proposed the correlation problem, for example. But that the correlation problem still has too much structure in a certain sense, right? And so I'm asking, like, can we eliminate all classically recognizable structure and still have a quantum speed up? Okay, so now a closely related question would ask, given an n-qubit, m-gate random quantum circuit, how many more gates must we add on to the end of it in order to get a peaked circuit, right? So now, like, I'm fixing the beginning of the circuit, right? And I'm asking, you can add an appendix now, right? Your goal is to make the circuit peaked using an appendix which is as small as possible, as small as you can make it. Okay, how small can you make it? Well, it's clear that you can always make your circuit peak by adding m more gates. How do you do that? You invert, right? You just invert the original circuit. Okay. Now, by using results about random quantum circuits giving you T designs, it is possible to show that the number of gates that you have to add onto the end in order to get a peaked circuit, is at least a polynomial in the original number of gates. I think at least m to the 1/5 power or something like that. Okay, but that's a very weak lower bound, right? And I really care, like, can you make the circuit peaked by adding only m over 2 gates? Really anything much less than m, right? And so this is a way of asking, like, if I look at the output of my random m gate quantum circuit, like, does it have sort of any interesting structure to it, right? That say a Haar random, pure state would not have had, other than just the obvious thing that, well, I could invert the circuit and go all the way back to the old 0 state, right? Is there anything short of that? Yes.
Yes. So in the previous slide, so you had started with 0
Mhm.
and you had x.
Mhm.
But these basis states seems to be, those peak distribution are exponentially smaller in the topology of those distributions.
They are,
So
yes.
then you can't just simply focus on starting from 0, whether you take some kind of a random path through the unitaries and you kind of close to that 0 instead of some other x.
Yeah. So yeah. So I mean, I do think, I think an excellent way to think about this is in terms of sort of, paths through Hilbert's space. It's like you're starting at the point all 0, right? And then you sort of wander around randomly, right? And now the question is, now I want to get back to something that I can recognize as I'm not completely in the wilds of Hilbert's space, right? I need some state with some efficiently classically recognizable property, right? And now I could always get back to such a state by just retracing my steps, just going back exactly the way that I came, right? But that's not interesting, right? So the question is there a better way to get back than that, right? A way where I've sort of taken a loop, right? And classically, I wouldn't notice anything special about the gates that make up that loop. But if I run it on my quantum computer, then I can see that I have gotten to a classically recognizable state. Right? So doesn't have to be the all 0 state. Some state that has some, on measurement has some property that I can easily tell it apart from just a random state.
So
Yeah.
my point was,
All right.
if you start with 0,
Yes.
you probably don't need the x, you can just have
That's
0.
right. So I don't understand.
So
I
if
just
you
don't get it.
have the
Yeah.
peak distribution,
Yeah.
the basis of the peak distribution
Yeah.
would be very sparse compared to all the other distributions.
Yes.
So from this distribution,
Yeah.
where 0 is the peak
Yeah.
state,
Yeah.
it's most likely, if you are close to it, you'll be close to the 0 than some other state.
Well,
close to the base.
I don't think that's necessarily true, because just by counting, there are so many more states that you might get to rather than just the 0 state, right? Maybe there would be some bias toward the 0 state, right? But there's so many others that and any of them are okay.
Scott,
Yeah.
question.
Yeah.
At least asymptotically, wouldn't the amplitude amplification balance strictly govern this?
So what would amplitude amplification give you here? That's not clear to me.
Okay.
I mean, because to run amplitude amplification, at least as I understand it, you would have to run the entire original circuit.
But why would you have to do that?
Because you're trying to get to a state that has a classically recognizable property. I don't know how to say it any better than that, right? I just yeah. Sorry. Okay. Yeah. Yeah.
So if you have a circuit that's random,
Yeah,
one
yeah.
option which is it's compressible.
Uh-huh.
That random circuits are compressible.
Yep.
And then you can do that.
Yeah.
There
But
are many
random
other
circuits
options.
are not compressible.
Do we know that?
Well, so there are these results that say that like circuit complexity increases linearly, right, as you apply a random circuit. Okay, the Nicole Younger-Halpern, and Jens Eisert et al., right, have recently shown such results, which give you a sort of incompressibility of randoms of the output states of random circuits.
Do we know
Yes.
that the measure of compressible circuits is sort of approaching 1?
You mean the measure of incompressible circuits?
Yeah, of incompressible.
I mean, in a sense, yes,
Yeah,
right?
okay.
Because you're picking each layer of gates independently of all the previous layers, right? So you're just adding entropy for each. Yeah. Okay. Right. I mean, how could it be compressible? Just by a counting argument. I mean, the non-trivial question here is about the output state of the circuit, right? But that's what the Younger-Halpern et al. Result talks about.
Okay, but the other question is,
Yeah.
do you need this to be efficient?
Do I need? Oh, well. Again, I'm trying to start by asking the existential question. Okay, I'm just asking, do these things exist? Okay, if they exist, then we can ask the next question of how do we find them. But it's not even clear that what I'm looking for exists.
Yeah.
Okay, It's not even, yeah.
Yeah, what about if they don't exist in Hilbert's space? If Hilbert's space is flawed, so
If,
Hilbert's space is
if
flawed.
Hilbert's space is flawed, then, you know, Nobel Prizes for all of us. You know, I mean, you know, that's way more exciting than anything that I'm talking about here. And let's discover them, right? Right, then, you know, then you know, basically everything in this whole conference is out the window, and let's go explore whatever that other true thing is. Okay. So, yeah. Okay. So yeah, we could even ask what fraction of quantum circuits are peaked. You know, I have upper and lower bounds. Of course, it's an exponentially small fraction, but you know, I would like some tighter bounds. You know, and then of course there is the computational question. So how hard is it to sample a random peaked circuit? Or what about just a peaked circuit that is hard to distinguish from random? Okay, so you know, so these questions can be addressed numerically. So I've worked with a recently graduated PhD student at UT Austin named Yushuan Zhang, and so we have some preliminary data where we like looked for, you know, random, we looked at random circuits on these numbers of qubits with, I think, you know, initially 100 layers of random gates. And then we asked how many more gates would you have to add onto the end of these circuits in order to get something peaked? Or to say it a different way, fix the number of additional gates that you're going to add on. Like, let's say it's 50 or it's 33 or it's 25 layers of gates, and then optimize the peakedness. So, you know, try to make the output of the combined circuit, you know, as peaked as possible, right? Have some basis state output with as large a probability as possible. And what do you get? And the short answer, at least from our you know, we address this using, you know, local optimization heuristics, right, to search for the best possible appendix that makes your circuit as peaked as possible. And so there are surprisingly peaked circuits that you can find this way. For example, if I take 100 layers of gates, you know, on 12 qubits, and then I just add on 25 more layers of gates, like I can get something where a single basis state is output more than 10% of the time, right? And we've examined these circuits and we see no obvious structure in them whatsoever, okay? They look like they're, you know, at least to us, like they are just random circuits, right? There's no obvious cancellations you can do. It looks like you're just randomly wandering around in the Hilbert space, and then lo and behold, somehow you end up at this peaked state. Okay, so those things seem to exist. That's the good news for verifiable quantum supremacy. But the bad news is that the amount of peakness seems to be decreasing exponentially with n, the number of qubits. Yes.
For a random state instead, or is it
Yes, so
random circuit?
Excellent question. This does not work for a Haar random state. Okay, that's the surprising and interesting part, right? You can just prove analytically that if you had a Haar random state, then, you know, there would be no short appendix that you could add, you know, no short circuit that you could add onto it in order to measure anything about it that would differentiate it from the maximally mixed state, right? This is you know, just by you know, standard tail bounds, right? You can prove that sort of statement, right? And you know, and our numerical results are consistent with that as well. We checked, right? But somehow in the outputs of these random quantum circuits, there is some kind of structure there that is not shared by a Haar random state, right? We don't know what it is. You know, we don't know how to explain it, but numerically you find it. Okay, that's the good news. The bad news, again, is that it seems to decay exponentially with the number of qubits. Yes, Frank. Yeah.
I don't really understand. So doesn't that mean that actually these circuits are compressible? Is that like the same?
Well, it means that they're very slightly compressible in any case. Yeah, but you know, we've done a lot of selection to find on the appendix part. Okay, there's the initial random part, which is not compressible, and then there's the part that we're adding to the end, which of course will be a little bit compressible.
Yes, but you can always go back to the original state.
That's right. You could always do that. That's why it's so important here that the appendix is smaller than the original circuit, right?
No, but indeed.
Yeah,
But
yeah.
Even with the smaller parts, you can require that you end up with the all zero state.
But that's not clear, right? I take a random circuit with 100 layers of gates. Okay, it's not clear whether there should be any circuit with 50 gates that I can add, with 50 layers that I can add to the end of it that will get me to the all
No,
zero.
that's just a 1 qubit depth quantum circuit that maps any basis state to any other basis state. No, so
No,
you can just split that a bit.
that's not true. You have this entangled you have this entangled n qubit state. You're only allowed to apply unitary gates to it, right? You can't just force a qubit to be
No,
zero.
I know, but you can
All right.
force that the X is at the end the all zero state. At no cost.
Yeah, but that you could do by inverting the original circuit. It's not clear that you can do it any more succinctly than that.
I'm sorry,
Okay.
I think Scott would.
Yeah, I just don't understand.
What Frank is saying is
Yeah.
that if you just wanted to map X to 0,
Yeah.
then you can do it with one layer. And so if you have a superposition where X is overrepresented, then you can get to a superposition where 0 is overrepresented.
Oh, yes, yeah, fine. If you have peakness on one thing, like X, you could always map it to peakness on a different thing with just slightly more depth. Of course, that's true, yeah.
And therefore you have inverted your circuit,
No,
but compressed it.
well, yes. So I mean, again, a peaked circuit, because of being peaked, must be slightly compressible. I agreed to that. I said that. Okay, yeah.
What is your definition of random circuit here?
You pick a bunch of gates, each one independently, uniformly at random. Okay, you can have different ensembles. The differences between different random circuit ensembles might be relevant, but right now I'm not. I'm not sure what difference it will make. So I'm not fixing a choice, right? But we can pick randomly sets of qubits to apply the gates to. You fix a universal basis of 1 and 2 qubit gates. Choose gates randomly, independently from that basis, and yeah, that's it. You could also consider spatially local circuits, right? I mean, you could consider ensembles where you're on a 1D line or a 2D grid, and that would give you a slightly different question.
Those would approach basically this two design feature, which this.
Well, yeah. So random. We know that random quantum circuits give you T designs for arbitrarily large T. Okay, those are very non-trivial results that have been proved over the last decade. Okay. So I wanted to. How many minutes of was that?
I mean, I'm happy to have you continue.
Okay. Well, I just wanted to for spend a few minutes to talk about a different approach to sort of near-term quantum supremacy that I am hopeful can actually be done in the near future. And this is wouldn't it be awesome if we could do a quantum supremacy experiment that didn't depend on any unproved computational hardness assumption, right? Well, what does that even mean, right? Well, it's clear that we would have to change the question that we're asking a little bit, okay? But there is one domain in which we have proven exponential separations between quantum and classical complexity, and that is communication complexity, right? The number of qubits, let's say, that Alice has to send to Bob to allow Bob to decide some function can be exponentially less than the number of classical bits that he would need to send, even in any randomized protocol. Okay, and we have, seminal results to that effect by, Gavinsky, Kempe, Ron Raz et al. From a couple decades ago. Wouldn't it be nice if we could, experimentally sort of demonstrate those results? Okay, and in some sense, what we would be demonstrating is not that quantum computers can give us an exponential speed up in terms of, computation time, computing resources, but that they could give us, that sort of a general quantum state of n qubits sort of requires an exponential and n number of classical bits in order to describe it. right? We want a sort of direct experimental verification of that claim about quantum mechanics, which of course is directly related to, the central claims of quantum computing, even if slightly orthogonal to them. Yeah. Yes. So good. So there was work in 2018 which aimed to do exactly that, which used optics to do it. Okay. And the main issue with that work is that they I think I had talk about that on a future slide, but they demonstrated a communication complexity separation, but in order to do it, they had to use an enormous number of optical modes. Right, the number of optical modes would increase exponentially with the and so they're not demonstrating that this, that sort of an entangled state of n qubits, actually requires exponential and n classical information, right? And now that is the claim that I want to directly experimentally test, and and having run some numbers, I think that the hardware, like, where you can now do 2-qubit gates with 99.9% fidelity and things like that, I think that the hardware is just now at the point where this sort of experiment ought to be feasible. Okay, the classic separation between quantum and classical one-way communication complexity use this thing called the hidden matching problem, where Alice has an n-bit string X, Bob has a matching on the set from 1 to n. The way that I always remember it is, Alice knows for each of n people whether they're male or female. Bob knows who is dating whom, okay? And the goal is that, Alice has to send Bob a short message that lets Bob figure out for any one couple of his choice just whether they're same sex or opposite sex. Okay. Now, classically, sending square root of n bits to Bob is necessary and sufficient, basically because of the birthday paradox. Of course, the lower bound was non-trivial to prove. Quantumly, only log of n qubits are enough for this task. Okay, because Alice can send Bob a state like this one, that just encodes the whole n-bit string in superposition form. And then Bob, given that state, can measure it in a basis like this, which for each edge in his matching, I and j, has basis vectors I plus j and I minus j. And if he gets an I plus j vector, then he knows that I and j were a same-sex couple. And if he gets I minus j, then he knows that they were an opposite-sex couple. So that's the protocol. Okay, so recently in a paper just a few months ago by me and Harry Buhrman and William Kretschmer, we noticed a new implication of this communication complexity separation, which is, in some sense could have been realized at any point in the last 20 years or so, but I don't know why it wasn't. We say that if you look at FBQP, which is the relational problems that have polynomial time quantum algorithms, okay, and you give advice to that, which could be classical advice or quantum advice, then quantum advice is just unconditionally more powerful than classical advice, right? It is rare in complexity theory that you just have an unconditional separation between two classes, okay, but that is the case here. And it's very different from the situation if we were to look at decision problems. So like I showed 20 years ago that BQP with quantum advice is contained in post-BQP, BQP with post-selection, and with classical advice. Okay, I also showed that post-BQP is equal to PP. So that means that you can't separate quantum from classical advice on a decision problem without also showing that, like, BQP is different from, P-space or huge things like that. Okay, situation with relational problems that have many outputs is completely different. Okay, and we basically just used the hidden matching separation to show this. And there's one additional observation that you have to make, which is that the separation still works if Bob's input is small. So in a sense, you can de-randomize Bob's input. And, it doesn't have to be an arbitrary matching. It can be a succinctly described matching. And the separation is still true. Okay, so my proposal is basically to use this kind of thing, this separation between quantum advice and classical advice with respect to relational problems, and demonstrate it experimentally. Okay, so you want to prepare some n-qubit state psi, and then measure it, where the measurement basis will only be chosen after the state is prepared. Right, so there could be many possible measurement bases, and in some sense, nature at the time that it's preparing psi will not yet know which measurement basis is going to be chosen. Kind of like in the Bell inequality, experiments, right? Won't know, and now we'll pick a measurement basis. We'll repeat many times with the same state and with different measurement bases. We'll collect all the results. Okay, we'll crunch them with our classical computer, and now we're going to try to make an argument that if we had any secretly classical description of psi that was sufficient to explain all of those measurement results, then it would have required exponentially many classical bits, okay, even for a probabilistic description. Right? And this is exactly the kind of thing that one-way communication complexity lets you do. For example, maybe with 20 qubits, we'll be able to check that any classical description of them would have needed at least 100 classical bits, okay, or some some number greater than 20 in any case. I don't think because of experimental limitations, it's not going to be 2 to the 20th power, right? But it could be something more than 20, okay, and and you could use the hidden matching algorithm from the last slide. But I think that to really make this practical, we want to design a new one-way communication complexity task that is specifically suited to doing this with an experiment. Okay, so I think you want to do something like linear cross entropy, where you're applying a random circuit to the all zero state. You're then measuring the output state in a basis that is chosen on the fly. If you use hidden matching, then it could look like this. But I think the measurement circuit might just look like you measure each qubit independently in randomly chosen bases, right? Or it could even be we apply a second random circuit. Okay, and then the test of the outcome could be look something like linear cross entropy benchmarking, right? So it's like still random circuits, still linear cross entropy benchmarking to check the outputs, but the interpretation of what we're doing is now completely different, right? We're now trying to show a communication complexity separation. Okay, and I've talked to the people at Quantinuum about this, who it looks like with 20 qubits with 99.9% all-to-all fidelity, you could do something like this. And I think it's great that there is interest in doing this type of experiment. But what is lagging right now is the theory. We need not just an asymptotic separation, but we need one that is tight enough that we can get concrete numbers for, let's say, 20 qubits that would give us the separation that we want. So another, the last idea that I just learned a few weeks ago is you could hope to verify random circuit sampling by just repeating it over and over and over again, like trillions of times, and just looking for a collision in the output, right? Looking for the same output occurring twice, which takes exponential time, but because of the birthday paradox, the time until a collision is only 2 to the n over 2, right? Not 2 to the n, and when n is 50 or 60, this might work. So I worked with Andrea Mari, and a back of the envelope calculation suggests that with current hardware, you might have to run for like a few months run your superconducting quantum computer, and then you would collect enough collisions that you could actually do statistical analysis on it and have evidence for quantum supremacy, without having to calculate a difficult linear cross entropy benchmark. So possibly worth it. I'm not sure. So, the question that I'm always trying to ask here is sort of, is there a law of conservation of weirdness? That sort of for every problem that admits an exponential quantum speedup, there must be some weirdness in its detailed statement, which the quantum algorithm exploits to focus amplitude on the rare right answers. How non-weird can we make it? All right, so thanks. Yeah.
Can you go back to your Venn diagram?
Yes.
Please. Thank you. There it is.
Yes.
Oh, there we go. Well, I would like to say that the QAOA also fits into the other box with boson sampling and random circuit sampling, because the QAOA at its shallowest depth has supremacy on random instances. But and it's proved at exactly the same level that you prove random circuit sampling.
That is true, but if we use QAOA in that mode, then we give up on the efficiently verifiable.
Well, that's right, but I'm
Okay,
saying,
so then we're still back here. We're still not in here.
I agree with
That's
that.
the problem.
But I think it's sort of fascinating.
Yeah.
that the QAOA, if you look at its shallowest depth, and you have the Sherrington-Kirkpatrick rule, let's say, and you set the parameter, only the shallowest depth, so there's two parameters, gamma and beta, and you actually will have anti-concentration, and you'll be able to prove that you have a circuit. But on the other hand, if you want to find a good string, meaning one whose energy is high, then you have to set the parameter to a corner in the parameter space. So the same algorithm at the same depth has both those things depending on the parameters.
Other questions?
Yeah.
Yeah, I just had a quick question about the kind of collision-based verification.
Yeah, sure.
I guess my question is I guess there must be some step I'm missing or something, because it's very easy, or maybe I think too adversarially like a cryptographer, but it's very easy, of course, for me to come up with something that produces collisions. I can just reverse the same string twice.
That's true.
How do I know that my circuit isn't just doing that by accident, sort of?
That's true. No, I mean, so this is not a way to sort of get how to say it. I mean, yeah, you could just substitute a trivial circuit, that is peaked, for example, that always outputs the same thing, right? But if what you were worried about is, was specifically that, you are just generating the uniform, distribution, let's say, which is, in practice is, one of, maybe the main worry, right, or one of them, then, you could rule that out, right? And you could even estimate the degree of, you could even estimate the fidelity of your circuit in this way, right, without having to do the hard classical computation. So I thought it was kind of cute, but maybe it's not more than that.
No, I mean, I guess if you have sufficient confidence in your noise model that it isn't doing something weirdly biased like that, then you actually, can be really confident something.
Yeah. No, I mean, it's kind of an obvious idea, but then the interesting part was you can run the numbers and you get out an answer that's on the scale of months, which is, maybe doable, right? Yeah.
In your experimental results on peak circuits,
yes.
Did you get any sense of the prevalence of those peak circuits? So you picked a random.
Yeah. So I mean, in some sense, the way that we're doing it is using local optimization to look for a peaked circuit. So it doesn't really tell you what fraction of circuits are peaked, right? We know that it's an exponentially small fraction, right? That's not hard to prove, right? We don't know exactly what, exponential fraction. As I said, I would love to have better balance. Yeah.
To what extent do you think this exponential decay is because of poorness of optimization, or is it
That's a good question. It could be that our optimization is just not good enough, right? But it could be that look, you can choose what to be surprised by, right? I was surprised that there is any peakness at all to find here, right? And I'm surprised that there is any exploitable structure in the output of a random quantum circuit. that differentiates it from a hard random state, right? And in some sense, the world feels saner to me, right? If that structure, it exists, but it decays exponentially with the number of qubits, right? If it doesn't decay, then that is awesome. That's awesome news for NISQ quantum supremacy, right? And then the circuits that we want are really out there to be found, and we just have to figure out how to efficiently find them.
We take the rest of the questions offline
Yeah.
and take a break.
Yep.